Welcome. In this session, we will solve some examples using discrete time Fourier transform. So, based on discrete time Fourier transform, we will solve some examples. So, let's start. So, first of all, before we solve the example, let's revisit what is Fourier transform. We can express any sequence x of n, which is a discrete time sequence, as a weighted sum of complex exponentials. So this is the formula. So we can express x of n as a weighted sum of complex exponentials. This is the Fourier transform. Now the what is x of omega? Where x of omega is summation n running from minus infinity to infinity x of n e raised to power minus j omega n. So this one is referred as Fourier transform. This one is referred as discrete time Fourier transform. So this is discrete. So this is referred as discrete time Fourier transform expression, and this is referred as inverse discrete time Fourier transform expression. Now, whether we say x of n or x of omega, it means one and the same. This is the frequency domain expression. This is the time domain expression of x of n. All right, let's solve some examples. So if x of n is given to us from these expressions, if x of n is given to us, we can obtain x of omega. If x of omega is given to us, we can obtain x of n. So let's start with this expression. Let's start with this. So let's solve some examples. So let's suppose x of n is this sequence 1, 2, 3, 4, 3, 2, 1. So this is the expression. So x of 0 is 1, x of 1 is 2, x of 2 is 3, x of 3 is 4, x of 4 is 3, x of 5 is 2, x of 6 is 1, and the rest of the samples are 0. So we'll obtain discrete time Fourier transform of this sequence. Discrete time Fourier transform of this sequence is given by this x of n e raised to power minus j omega n. Now substituting the values of x of n, we will obtain, first of all, x of n is non-zero from 0 to 5. 1, 2, 3, 4, 5, 6, 6, 6. That's fine. So it will be summation will vary from 0 to 6, x of n e raised to power minus j omega n. Now substitute values are different values of n. We will obtain x of 0 e raised to power 0 and n equal to 0. Put n equal to 1. So minus j omega n is 1 plus x of 2 e raised to power minus j omega 2 plus x of 3 e raised to power minus j omega 3 when n is 3 plus x of 4 e raised to power minus j omega 4 plus x of 5 e raised to power minus j omega 5 plus x of 6 e raised to power minus j omega 6. And is 6. Rest of the samples are 0. Substitute the value of x of 0, x of 1, x of 2, 3, x of 4, x of 5, and x of 6. These are given here. So substituting the values, we obtain, so we'll get x of omega as x of 0 is 1, e raised to power 1 is 1, so it will be 1. X of 1 is 2, this will be e raised to power minus j omega. Plus x of 2 is 3, this will be e raised to power minus 2j omega plus 4, x of 3 is 4, e raised to power minus 3j omega here plus x of, substituting the value of x of 5, x of 4, x of 4 is 3, the e raised to power minus j omega 4 plus Let me rewrite this value, which is 4j omega 2 e raised power minus 5j omega plus 1 e raised power minus 6j omega. And rest all the number 0. So this is the discrete time Fourier transform of the given sequence. Now you can simplify this. You can take some terms common and simplify this. Let's not do this here. So this is our discrete time Fourier transform of the given sequence. All right. Now let's plot it. Let's plot this. Now remember, x of omega will have magnitude as well as phase. So we'll have to plot the magnitude and phase. We'll not determine that here, but we'll see this in MATLAB. How do we do this in MATLAB? How about phase and there's magnitude will vary in MATLAB. Okay, let me switch to MATLAB to show you this. So let me switch to MATLAB to show you the magnitude and phase plot like this. Alright. So MATLAB has an inbuilt function to do this. That's called fplot. Fplot means frequency plot of this. Now we want the magnitude. Magnitude is denoted by ABS, and we know the function is this. Please pay attention to this. The function 1 plus 2 is j equals to some j omega 3 is some omega and so on. So for this first trial, for the absolute value means magnitude of it. So it is 1 plus 2 times exponential e to the power in the term of exp in MATLAB minus 3 so 1 j plus 3 minus exponential of minus 2 j minus 1. Exp plus 4 minus exp. Exp means e to the power of the value minus 3 j times I think it is j, this is 3j, this is 3j, and plus 3 is 3 minus 4 and j and plus 2 and e to the power of minus 5 and j omega plus 4 minus 2 exponential minus 6 minus j minus push to the and let's say the frequency range. The frequency range is minus 5 to 5, and let's the color of this plot will be blue. Will be simply blue. We don't need it here, but let's make it the fancier line with a history. That's what the line with the plot. So if you do this plot, let's make before I show you the plot. Let me turn on the board and show you it. Have a look. This is the magnitude plot of the given. This is the magnitude plot of the Fourier transform that we can discrete time Fourier transform. So this is how you plot this magnitude plot in MATLAB. Now let me show you how to plot the phase plot. Let me show you how to do the phase plot. So before I show you the phase plot, what we will do is our given sequence is 1, 2, 3, 4, 1. So this is the given sequence. And n is there in 6. Let's we'll do is plot the same. So we have three plots on this. So this is E X red and the line with it should be line with it should be this is this so they are going to start the second one. So 2, 1, 1. So this is subplot. They have all the plots in this one. The subplot and command the plot in comma x means I want to plot the time dimension as well. So we can say that I want to plot this is in red and the line with it will be 3 this is the plot, this is the step plot. So that we plot the discrete function in the step. Right, so we can do also. This is our x. So this is our boundary. So and then sigma of sigma. So this is our sigma. Now let me plot the numbers. Second plot. Will be the plot. So this will be the second plot on that window, and the third plot on the plot here. This is the magnitude plot. Phase plot also. The third plot will be phase. To plot the phase, we use Lagrange's inbuilt function that's the correct angle. And then simply phase, and then we so this is the phase plot function. Let me show you what I have done. Now look at this. This is our original signal. This is our original time domain signal. This is it is magnitude plot and the frequency domain magnitude plot. And this is the phase plot. This is the phase plot of the spectrum. So this is the magnitude plot of the spectrum. This is the phase plot of the spectrum. It varies linearly. Then it has some those transitions at some frequencies. You can see. So transitions. All right. So this is how we plot. And this is how we plot the this magnitude and phase plot of discrete time for a transforming model. Alright, now let me go back. Now have a look at this. Please pay attention to this. You can see that we take discrete time sinusoids from minus pi to pi. This is very, very interesting. As I already said, if you remember in sampling point, we said the discrete time sequence has its frequency varying from minus pi to pi, or in short from 0 to 2 pi. Means the maximum frequency will vary from minus pi to pi. That's why we are combining the sinusoids only from minus pi to pi. Now, to prove this result, what we are going to do, we are going to change the frequency from we are going to plot the magnitude spectrum not from minus pi to pi, but suppose from minus pi to pi, or minus 2 pi to plus 2 pi. Let's see what will happen to the magnitude spectrum. So if we try to plot this, we will plot that. What we'll do, we'll go back to MATLAB and let me plot the magnitude spectrum. Let me get it back first. Then on this will plot the magnitude plot. This time the magnitude plot will plot, let's suppose from minus 3 pi to plus 3. Let's suppose. So if we try to do this, what will happen to the spectrum, the magnitude spectrum. And if we do this, Fourier. And let me show you the phase out. What will happen to the phase out? So phase plot. What will happen to both magnitudes? Phase. And let me show you the plot one. You can see this is simply the repetition of the same spectrum. Have a look at this. Now this is plotted from minus 3 pi to plus 3 pi. You can see it is simply the repetition of the spectrum from minus pi to pi. Here is minus pi, somewhere here, and this is pi. You can see these are just the repetition of this the same spectrum. So it is the repetition of the same spectrum. So whatever you have got in from minus pi to pi, now it is simply the repetition of that. You can have a look and see. And that's magnitude and phase spectrum is repeated. Alright, I hope you have got the idea. I think I did it wrong for phase plot. I think I did it wrong. Let me go back. I didn't change the phase plot. Yes, I didn't change the phase plot axis. I didn't change it. Should have done it wrong. Let's click on it. So let me do it. Just click on it. Click on it. You can see it's simply the repetition of the spectrum, magnitude spectrum as well as the phase spectrum is repeated. Whatever you have, whatever value you have from minus pi to plus pi, same spectrum gets repeated. Alright? I hope you understood. That's why the discrete time Fourier transform, remember this, discrete time Fourier transform is a periodic spectrum. The spectrum will repeat. So it's a periodic spectrum, and the period is 2 pi or simply from minus pi to pi. So discrete time is x of omega. Discrete, sorry, discrete time Fourier transform is periodic in nature, and the period is 2 pi. And the period is 2 pi. I hope you have got the idea. Now, here's a little assignment for you guys. Please try to do this at your place. Suppose x of n is 1, 1, 1, 1, 1. Determine x of omega. Determine x of omega of the signal. If the sequence is 1, 1, 1, 1, determine x of omega, and then plot the magnitude spectrum in this x of capital omega, x of omega and phase of this. So plot this in MATLAB. So second assignment plot. Now second assignment for you guys is this first. Second assignment is if x of n is now 1, 2, 3, 4, 3, 2, 1, same sequence with 2 zeros. So this is the same sequence, but now we have added. So do this means plot the get the x of omega first, then plot that in MATLAB means magnitude spectrum and phase spectrum. So if x of omega is 1, 0, 1, 0, plot x of omega for these and plot the magnitude and phase spectrum. Alright, let me end this session here. In the next session, we'll do solve some more examples. Okay.